Hello everyone, in the video today we're going to talk about improper integrals. There are two types. The first type is of type 1. These are usually easier to tell because infinity is in one or more of the bounds of your integral. So it needs to be continuous on those bounds, and you'll replace any infinities with other variables, usually a and b for like the top and bottom bound, and then have the limit as that approaches infinity. So if you have an integral from a to infinity of f of x, then we will rewrite it first with the limit as b approaches infinity of that same integral, but replacing the top bound with the b. Likewise, if you're approaching negative infinity, we'll have our integral from negative infinity to b of f of x be the same as the limit, this time as a. Usually we'll write a approaches negative infinity. This is just another way of saying it. A approaches infinity of negative a to the b, or you could say the limit as a approaches negative infinity of a to b, the integral from a to b of f of x. And then if it's continuous from negative infinity to infinity, then you can split it up somewhere in the middle, and then apply the same two rules you just did for 1 and 2. So 3 kind of just breaks up into the same rules for 1 and 2. Then type 2 is a little bit harder to see, and that's when you're integrating over some discontinuity. So if f of x is continuous on a to b and discontinuous at a, then the integral from a to b, you'll take the limit as c approaches a from the right, from c to a. Right. I think this should be b. I think they made a mistake there. It should be from c to b here instead of c to a. That makes more sense. Then if f of x is continuous on a to b and discontinuous at b, then the integral from a to b of f of x dx, we're going to take the limit as b approaches from the left. Wow, they made a lot of mistakes here because this is a and c. But if it's continuous at the upper bound, oh no, this is fine. From a to b, but b is coming from the left and you're approaching from c. Easier to do when there's actual numbers. And then if it's continuous somewhere in the middle, these are the hardest to see, then you need to split it up at that point of discontinuity. So if it's discontinuous at c, you're going to break it up at c. Cool beans. Let's just run through some examples. I think it'll be easier after that. So evaluate integral from 0 to infinity of 1 over x squared plus 3x plus 2. We know this is type 1 because it has infinity in the bounds. First thing we're going to do is rewrite it with the limit as b approaches infinity, integral from 0 to b of the same thing. Then if it's complex like this one is, where we have to do some extra work, it's not just an obvious integral, we'll just take it out as an indefinite integral and then put it back in later. So we can factor this to x squared plus 3x plus 2 equals x plus 2 times x plus 1. And then this becomes a partial fractions problem. So I'll take out that 1 over x plus 2 x plus 1. That's the same as a over x plus 2 plus b over x plus 1. We'll multiply both sides of this equation by those two factors. And then we will simplify. So when we simplify, on the left, everything will cancel. We'll be left with 1. On the right, we'll get a times x plus 1 plus b times x plus 2. And this is easy enough that we can just choose values for x. So if x is negative 1, then we get the result b is 1. If x is negative 2 and the b goes away, we get a is negative 1. So then we can rewrite this as the integral from 1 over x plus 1 minus 1 over x plus 2. Changing the orders because I want the positive one to go first. And this is easy enough to integrate. We'll get natural log x plus 1 minus natural log x plus 2. And normally we say you don't need to worry about combining the logs, but in this case you do. Otherwise you'll get that this diverges, but that's not true. With log rules we can see that. So we'll combine this. They have the same base, so if we're subtracting on the outside we can divide on the inside. But natural log x plus 1 over x plus 2. Now let's put that back in. So we had the integral from 0 to b of this whole 1 over x squared plus 3x plus 2, but we just did that integral. And now we have natural log absolute value x plus 1 over x plus 2 that we need to evaluate from 0 to b. When we do that, we'll get natural log b plus 1 over b plus 2 minus natural log of 1 over 2. And we know on the inside, the b's on the top and the bottom, like the highest degree is 1 on the top, highest degree is 1 on the bottom, so we'll take their coefficients, which is just 1. and then minus natural log of 1/2. But natural log of 1 is 0, so we'll get 0 minus natural log of 1/2. But we can use log rules one more time to write that the negative we can put on the inside as an exponent, and then evaluate 1/2 to the negative 1, which is 2. So our final answer here will be that it converges to natural log absolute value 2, or just natural log of 2. Cool. Number 2, integral from 0 to 1 of 1 over 4y minus 1 dy. So this is easier to integrate, but we have to be a little bit careful because there is a discontinuity between 0 and 1. If y equals 1/4, then we get 1 over 0, which is no good. So we're going to rewrite it as the limit b approaches negative 1/4 from the left, from 0 to 1/4, so it's like the first half of it, of our integral, plus the limit as we approach from the right, 1/4 from the right, going from c to 1. So we're splitting it up. I like to use different letters here, but I think you can use the same and it's okay. I just prefer to use different letters like b and c. Next, we are going to integrate. Luckily for us, this is a rather doable integral. Remember that if you do u substitution, you'll make u 4y minus 1, and then du is 4 dy, but there is no 4 here, and that's why we divide by the 4 on the outside. And you can always double check by taking the derivative of this and seeing that you get the 4's to cancel out from chain rule. But we'll get 1/4 natural log 4y minus 1 for both of these sections, but we need to plug in the bounds, 0 and b, c and 1. So we'll get this big old mess. Limit as b approaches 1/4 from the left, 1/4 ln b minus 1, and then 1/4, when we plug in 0 here, we'll just get natural log of negative 1. This is going to end up just being 0, because natural log of 1 is 0. Likewise here, when we plug in 1, we'll get 1/4 natural log of 3, minus 1/4 natural log of 4c minus 1. So let's simplify this a little bit more. If we take the limit as b approaches 1/4 from the left, we will get this natural log to diverge. So the area, so this is saying the area in this section diverges. And really, as soon as we get that, we pretty much know the whole thing is going to diverge. Diverges. Cool. Example 3, negative infinity to infinity, x cubed e to the negative x to the 4th. We will rewrite it, splitting it at 0. I think I made a little mistake here. From negative infinity, this should be a to 0, and then b to infinity. Sorry, 0 to b. So I think I just copied and pasted this and then forgot to do it. So let's just fix that real quick. This should be that's fine, that's 0. This should be a, and this should be 0. So I just messed up those two, a and 0. Okay, we'll do u sub for this integral. U is negative x to the 4th. Du is negative 4x cubed. And that means there's no negative 4 here, so we'll divide by negative 4 on both sides, and we'll get negative 1/4 du equals x cubed dx. Let's sub back in, and we'll get this integral equivalent to e to the u du, which integrates very nicely to e to the u times that negative 1/4, and then we'll back substitute the value for u, negative x to the 4th. Okay. Here I have the bounds correct. That's good. So if we evaluate from a to 0 and then from 0 to b, this is what we'll get. And the big thing to remember here is that when we plug in negative infinity or positive infinity, it's being raised to the 4th power, which means it's going to be positive. The a to the 4th will be positive, but then we have the negative on the outside. That means that we'll have e to the negative infinity for both of them, and both of these terms will go to 0. Both of the things with e in it will go to 0, and then we're just left with these 1/4. So we got negative 1/4 plus a negative plus minus negative 1/4, so we'll add those together. Awesome, so the negative 1/4 plus the 1/4 will give us a 0 area for this one. Cool, last example. Integral from 0 to 1, natural log x over square root of x dx. This is type 2 again because there's no infinity in the bounds, but it is undefined at 0. Both of these functions are actually undefined at 0. So we'll take the limit as a approaches 0 from the right so that we're still in our interval. of the integral, just copying it down, but replacing that bottom bound with a. And then we're going to pull this out because it is going to be more complicated, not going to be a quick u-sub. We'll rewrite 1 over squared x as x to the negative 1/2, and then we can do integration by parts. So when we do that, we're going to pick natural log as u, x to the negative 1/2 dx as dv, and then take the derivative and integral respectively. 1 over x dx and 2x to the 1/2, because we add 1 to the exponent, and then we divide by it. Dividing by 1/2 is the same as multiplying by 2. So we'll do uv minus the integral of v du. I'm just rewriting this x to the 1/2 as square root, but keeping it as the power in the exponent in the integral so that I can do power rule again. Here we can simplify it by dividing. So subtract 1, we'll get 2x to the negative 1/2. And when we integrate that, we'll get a 2 squared x natural log x minus 4 root x. You can, if you want, factor out the 2 root x. In this example, I didn't do that. But let's finish this up. So we plug it back in, but we still need to evaluate from a to 1. So we'll plug those in. And I'm just replacing the x's with 1s, and then in parentheses, subtracting, replacing everything with a's. So on the left, the natural log of 1 will disappear. We'll get a negative 4 from the negative 4 times 1. And then this 2 natural log a natural log of a, 2 squared a natural log of a minus 4 root a. So the 4 root a is obviously going to go to 0, but we need to do something weird with this 2 root a natural log a. So I'm going to take it out as like a separate problem, scrap work, and replace the a's with x's just because it's easier for me to think about it that way. So if x goes to 0 from the right, that means for root x, we approach 0. But for natural log x, it means we approach negative infinity. And this is indeterminate form. But not an indeterminate form that we can do anything with, so we need to rewrite this. We are going to rewrite it with the 2 natural log x on top, and then rewrite the rad x as 1 over rad x in the denominator. And then this time, we will get infinity over infinity, or there's a negative there. So negative infinity over infinity. And that means we can use L'Hopital's rule, taking the derivative of the top and the bottom. When we do that, we will get a 2 over x from the top, and then a negative 1/2 x to the negative 3/2 on the bottom. But we can simplify that, bring this up and multiply the 2 with the 2, so negative 4. And then bring this up, you'll have x to the 3/2 minus 1 is x to the 1/2, which is square root of x. And that all goes to 0. So because that all goes to 0, the only thing that's left is the negative 4. So the integral from 0 to 1 of natural log x over root x dx is negative 4. The solutions for this problem on the sheet say 0, but that is incorrect. It is negative 4. All right, hopefully you are feeling a little bit more comfortable with improper integrals. I know I burned through these examples pretty quickly, but there are plenty more practice problems where these came from. All right, I'll see y'all in the next video.